Welcome to the third lecture on communication interfaces for embedded systems. Communication interfaces are needed for exchanging information with another integrated circuit or other external devices. There are multiple standards of communication interfaces with which an embedded system talks to another system or internet or whatever. So typically the entire set of communication interfaces may be divided into two broad categories. One is the parallel communication, where multiple bits are transferred at a time, which requires only a single clock pulse to transmit the data. But then as we understand that it requires multiple lines to transmit multiple bits at the same time parallelly. So a better approach would be to have a serial communication mechanism where a single bit is transferred at a time over multiple clock pulses. Serial communication is again divisible into two broad categories: the synchronous communication, in which the transmitter and receiver operate on a common clock signal. On the other hand, in case of asynchronous communication, no clock is transmitted. So in that case, the transmitter and receiver can have their own clock, and they most commonly do not talk to each other about the clock signal. Asynchronous communication is popularly used for most embedded systems. It consists of a simple and universal communication scheme where there's a hardware called Universal Asynchronous Receiver Transmitter, UART, which is built into many microcontrollers. Even if UART is not available, it can be emulated easily with a timer assisted by software. This asynchronous communication usually requires a single wire for each transmission direction plus a common ground wire. Most of the general purpose connections are full duplex. That means data can be sent simultaneously in both directions, and often it is used for connecting two end devices, and it's not a bus. So in asynchronous communication is typically a serial communication without clock signal. So we don't really have the transmitter and receiver synchronized with the help of a clock signal. They can have their own clock each, and so it requires some kind of a handshaking mechanism to ensure a reliable transfer of data from the transmitter to the receiver. Now, in order to synchronize the transmission with the two ends which run on independent clocks, it is suggested to use absolute or real-time clock and then transmit short data at a time. Typically, the convention is that we transmit 1 byte of data at a time, but then there has to be markers to indicate the start of transmission and end of transmission. So this that is basically ensured with the help of start and stop bits. And similarly, we also need to ensure that there is no flipping of bits at the time of transmission. So there is a parity bit also being provided in addition to the start and stop bits. So data is usually sent in short frames, typically consists of a single byte, and a high to low transition basically indicates the start of a frame, and then at the end of the frame you have a stop bit and a parity bit, which basically indicates that the data frame has ended. So when it comes to referring to the transmission speed, there are we typically specify the transmission speed in terms of the baud rate, which basically refers to the number of signal changes per unit time. So when we say 9600 baud, it basically refers to 9600 times the number of signal changes per second. In RS-232 standard, each signal change represents 1 bit, so bit rate and baud rate are same. So since each bit is accompanied by each 8 bits of data frame are accompanied by a start and stop bit, so the maximum data rate is only 8 by 10 times the baud rate. The final sample is taken 9.5 bit periods after the initial falling edge and must lie within the stop bit. The permissible error is therefore plus minus 0.5 bit period in 9.5 periods, plus minus, or that means plus minus 5%. There may be many errors in both transmitter and receiver, so it should be accurate to within about plus minus 2%. Universal synchronous asynchronous receiver transmitter, or USART, is an IC chip that is popularly used for serial data communication. It consists of a programmable peripheral designed for synchronous asynchronous serial data communication packaged in a 28-pin chip. It receives parallel data from the CPU and transmits serial data after conversion. At the receiver end, it receives serial data from outside and transmits parallel data to the CPU after conversion. So this is the pin diagram of 8251A, which has been developed by Intel Corporation and is popularly used in most of the microcontroller boards even today. So if you see the block diagram of the 8251A, it consists of the transmit buffer, which basically receives the data from the data bus, and then uses a serial shifting to shift the data to the serial lines for transmission. Similarly, the receiver buffer receives the serial data and then provides the parallel data to the data bus at the same time. So apart from this, there are also modem control for controlling the rate of transfer of data and whether it is a data terminal or data communication equipment, and there are also the control unit to issue the control signals to the different components. So this is about USART, and this is the end of today's lecture. Thank you.